Is true, I suppose.
Okay.
Twitch looks really nice right now, so it's just the Discord.
Yeah, so it's on better text quality. Is that what you want?
Yeah. It's like the screen is too big. What's the deal here? Is anybody else seeing this? It's like Adam's screen is
Just a second.
being
This may be it.
rendered. Oh wow, yeah, it's getting better.
Yeah, okay. I see what the problem was.
Yeah,
Okay, now it's
like streaming your whole like screen. It looks like it's streaming some window. I don't know if
corner.
it's intentional.
Yeah, it's like the top left corner is only being streamed.
Wait, what? All right. Have we ever just thought? Oh, I see. Have we ever thought that maybe just these programs suck? Has anyone?
Have you, or are you using the OBS virtual cam at all, or do you have that added on?
Just a second. Okay, is that better?
Yeah, that's better, but it's this tinier screen now.
That's what I had it last week.
The quality is better, yeah.
Okay. That is what I wanted. Okay, can somebody double check that the sound is coming in on Twitch? From Discord, actually, is really what. Or I can do that. Just a second. Zion, say stuff.
Yeah, I can hear you on Twitch.
Can you hear yourself, though?
Can anybody hear me speaking through Twitch?
Yes, I can hear myself on Twitch.
Nice. That's good.
Beautiful. All right. I think we
cool.
are good. Do you want to do like an intro-y thing, or?
Yeah. I'll do the intro for you.
Cool.
Thanks again, everybody, for coming this week. Some of you still trickling in. I hope you guys are having a good week. This weekend, we don't have any major CTF coming up. There are other smaller CTFs going on. Always feel free to self-organize. If you guys want to play by yourself, you can always take up the name ASU Hacking Club if you like, or even Shellfish if you're gonna go hard. Other than that, there is Flare-On CTF that has been running for the last, 3 weeks or so. We announced it in the CTF announcements channel. If you want to play, you can go in. Well, you have to. It's a single person CTF, but we have a discussion channel for like light discussion. Though I'm sure others will be more than willing to help you out if you're really new to this. So go check it out. Lastly, there is another CTF coming up in 2 weeks, or about a week and a half from right now. It's Tasteless CTF, and we will be playing all out on that CTF. So come and play it if you are interested.
What are the times of Tasteless, and how long does it last?
Tasteless lasts 24 hours. It's next weekend, not this one, next weekend on Friday. The beginning hour is still questionable right now. The organizers are still changing it, so it could really be any time.
Very tasteless of them.
Very tasteless of them. It's a binary heavy CTF, so it should be a lot of fun. Also, congrats to the 2 new people who got on the members list. I think that was you, boy, and someone else. Or it was who? Oh, Woody and Jay Nathan. Good work, guys. You are official members. If you haven't taken a stab at the member challenge yet, go and check it out and get your membership. That's all we got. And take it away, Adam.
Cool. All right, thanks, Zion. Today we're gonna kick off by continuing what we talked about last week, so getting more familiar with the command line. And so, if I can do this in a way that doesn't leak flags. Actually, Zion, could you open up the pipes challenge and the columns and rows challenge? That way I don't accidentally give anything away on my side. Thank you.
Yeah. I've always worried about that, about about looking at the admin.
Exactly.
Admin page. Yeah.
That's why Discord warns you when you're streaming. That way you know.
The pipes is open. It's up now. And the columns and rows is up now as well. All right.
Cool. So these are two on the definitely the way simpler side of the challenges, but the goal here is to get you familiar with the command line. So I want you to, urge you, if you are still new to these things, don't try to do this by hand. I really want you to try to do this by creating like a series of pipes in the command line to do this. So for instance, here's the pipes challenge. So basically it starts off with a description of how the flag was encoded. So the flag first had all zeros replaced with a capital O, all ones replaced with a lowercase l, and all e's replaced with a 3. And then the flag was base 64 encoded. And here's the output. So basically you're getting the output of the sequence of operations. So figure out how to reverse these sequence of operations to get you the flag. The commands that you need to know and to learn how to do are the base 64 command, and the tr command is a great one. And so, of course, let me make this. Right, so again, just like we've been talking about, what you'll want to do, read the base 64 command, figure out how to make base 64 decode. Figure out how to do that. And then TR is to translate characters. So it's actually a really easy and nice tool to replace one character with another. So do that, reverse this, take this, base 64 decode it, replace all the characters the other way, and submit the flag. And then for the other challenge, columns and rows. So this is this will give you a file. So you'll download this file. Again, it does not have a file extension because file extensions are meaningless and we don't care about them. So the idea here is, so what you want to do is download it just like I'm doing. I'm actually on a different machine here, but I think I have the same thing. Nope. Challenges, boom. There we go. So first thing we'll always want to run on any kind of binary or challenge we get in a CTF is figuring out what it is, right? And just like we said, the file extension doesn't matter, but this is telling me that columns and rows is a bunch of ASCII text. So I can use my handy dandy less command to start looking at it. And I can see, oh, wow, that is a jumble of text, right? So if this was a real CTF, we may not know where the flag is. Maybe the flag is one of these rows is a flag. Maybe every other character is a flag, something. It's hard to tell. And so we'd have to go back to here. We'd read the description. So the flag is located in the 10th column of this page. So, and I guess of this page, I meant of this file. So using the command line only get the flag. So the two commands I want you to look at for this challenge are cut and tr. So we'll look up cut. Cut is super cool way of extracting certain bytes from the command line. So you can use it to select only certain bytes, only characters. I use it a ton. So the main way to use cut is for to get different fields. So basically, let me show you an example. So by default, -e, so Adam T. So you've probably ran a lot of commands that show you kind of output in tab separated values. And the purpose of cut is really to get those. So if I wanted to extract from this Adam tab Dupay tab foo, if I wanted to select the third column, I can pipe that through there and it will separate it by tabs and give me the third column there. So I use this a lot when like parsing command output or output from other programs to select things. It's actually really helpful to use and to do. So yeah, what we're gonna do now is work on these problems. So I'm gonna switch this over maybe. And I think Twitch will see that, but the Discord does not. Is that correct? Yeah, okay, cool.
That is correct.
I can see it on Twitch.
Good. Okay, that's what I wanted. So check out Twitch to get the meeting flag, and work on the challenges. That's the goal right now. So we'll do that for, I don't know, half hour, 20 minutes until we get roughly 10-ish, 11-ish, 12-ish or so solves. Feel free, ask questions in chat, ask questions on voice. Happy to help. And while you guys do that, I'm going to set up for the next part, which we're going to be talking about. We're going to dig into assembly and start coding stuff. Any questions? Feels weird to not say anything while streaming. Oh, see my tricky way of forcing you guys to look at the Twitch stream, to put a flag on there. Easy, you set timer for 20 minutes? Yeah, good question in the chat. So we'll be in the next part. We're diving into assembly, and we're gonna write code that will run on x86-64 Linux. So you'll need access to a Linux system to do that correctly. So Zion's gonna link in the meeting chat the link to setting up a virtual machine, which you can get running now. If you know that's a bit much. The other thing, if you could do Zion, is drop. You should be able to actually SSH into ASU's general to access it there.
Then they would have to have SSH client though.
Yes.
Yeah.
That should be. I mean, everybody's been using the terminal. I think it'd be only people who are using the like cmd.exe on Windows. Remember, if you're stuck, to ask for help. We're happy to end here to help you get unstuck. BRB, folks. All right, let's check on the status. All right, pipes 12 sols, great job. Columns and rows 4 sols, very cool. Nice. 15 sols of pipes. Great job. All right, it's been 15-ish minutes, maybe a little bit longer, more like 20. Let's look at this, see where people are. I think people are getting there, which is super cool. All right, Pipes has 18 solves. That's amazing. Column and rows is sitting at 10, so we'll wait, give it another 10 minutes and see how that goes. I posted some spoilers, hints for columns and rows in the chat, so feel free to check those out if you're stuck or ask questions. Happy to help. All right. Let's check where we are. Pipes, 20 solves. Amazing. Columns and rows, 14 solves. Cool. And I hope, as you're going through and solving these things, you're, kind of, this is where we're putting it all together, right? The understanding of how to pass options to something on the command line, how to read the man page, how to, those types of things. The more you do them over and over, the easier it becomes as you go. So you can kind of, now when I'm looking at unfamiliar software and looking at the man page, I kind of easily know what to look for and know how to skim it because I skimmed, I've read many of them, but yeah, this is great. Okay, let's give it, I'd like to see columns and rows get to 15. So it's at 14 right now. Let's get that last solve, number 15. I'll give you a shout out and we'll start coding and learning about assembly. So you're all experiencing this is the problem with having, security competitions be a sport because here we are waiting for this race, but we have absolutely no idea who's closer, who's going to get it. But we will be excited
That's what I'm saying.
when they do.
Checkpoint-based challenges.
Yeah, Davide.
Which is essentially, I guess, just more challenges in one challenge.
Right. From experience, it's very hard to ensure that one part of a challenge is solvable in the way you think and not, multiple ones all in one or.
Yeah, fair. But then that would be more suspenseful.
I mean,
if somebody didn't look
possibly.
like they were close and it
then just comes from
boom.
behind. Yeah.
Yeah. As opposed to like you have some kind of sanitizer that tells the hosts when they've started leaking addresses.
Mm-hmm.
And now they're like 1/3 the way there because they've leaked an address, and then they leak libc, so now they're 2/3 the way there.
We got it.
Oh.
54 NID, probably Andy, something like that. Great job. All right, cool. Let's go back to the normal stream. Look at this. I've got different scenes going on. Watch out, Zion. Tell Jan he better watch out.
Dang, you're a real streamer.
Yeah, I'm the streaming master. He's just a poor imitation of me.
Dang.
All right, but the question is the profile. There we go. Windowed projector. Boom. And now that's streaming. Now got that back on. Jan couldn't beat a doorbell. Sounds like a story for another time.
The Zoom doorbell.
Oh, yeah. Jeez. I mean, that doesn't even happen on my system. Why was it happening on his? Like, it's a setting you turn off. That's what I don't understand. I think it's very clear he just forgot to do it. All right. Cool. Although now I just threw shade on Jan, and now I'm going to steal his stuff. So, in a funny turn of events, I thought I already had slides prepared for like assembly language, and it turns out they were all for 32-bit x86, and so I don't want to teach that. I want to start us off on x86-64, and so I'm going to be using Jan's slides. And really kind of what we're going to do now, so we've learned a little bit about how to interact with the system. We've learned a bit about how the shell works. You've put together different shell commands. So I hope you're seeing now the real benefit of being able to combine these simple utilities like cut or base 64 decoding or character replacement. You can extend this to grep, so you can look for lines in a file that match a thing and then pull them out and do all kinds of really cool stuff by combining all these things. So what we're going to do now is, and it may surprise some of you if you've never really, thought about this before, but to actually be, to get really good at security, to be able to understand vulnerabilities, identify vulnerabilities in code, you really need to be a strong coder yourself. So, take all the chances you can to improve your coding skills in your class, really apply yourself, start early on your coding assignments. Don't look at it like like it's just a chore. Like, these are the things. The more you code, the better you get at it, and the better it will help you be a security analyst. And so where we're going to start out is at the very bottom of programming. This is kind of a new model. I haven't really taught in this way before, so I'm super excited to see how this plays out. So first we want to kind of understand, so really everything we do, so we write source code in some crazy high-level language, Python, JavaScript, Java, C or C++ or Rust or Go or whatever thing, right? The computer itself can't actually execute that, right? The computer can only execute binary instructions, and so in all cases, right, the code that we're writing doesn't actually get executed by the computer. It's first through a process either compiled, interpreted, or JITted, but it's essentially usually compiled. So we're going to mostly focus on C code. So the C program, you have a C compiler like GCC. It takes that code, it compiles it, and spits out literally ones and zeros that your CPU, right? What is a CPU? It's a chip made of silicone. I don't know how they make them. It's very complicated. That actually executes those instructions, and so the CPU is really at the heart of everything we do. And if you actually dig a little deeper, you'll find in your computer architecture courses that a CPU is made up of different gates. So we can actually see things in here that correspond to programming like we're familiar with. The ampersand symbol is an AND. So this would be if, and this is literally ones and zeros. So if A is 1 and B is 1, then the output Q here will be 1. Otherwise, if either A or B or both are 0, then the output of Q is 0. And we have all kinds of crazy operators. At the bottom is a negation. So if A is 1, Q is 0. If A is 0, Q is 1. And so these are all kinds of crazy logic gates that actually make up the CPU, which is honestly insane when you think about it, right? This is just, and if you anybody out there do any, I'm not a big Minecraft person, but anybody build any crazy computers or stuff in Minecraft? Anybody? What's called craft heads, block heads? Just dig big holes. Yeah, that sounds fun. Yeah, people have seen it on Reddit. Red stoners, that's hilarious. A calculator definitely counts. Yeah, so you're actually, what's super cool is you're building a computer based on a game where you're actually building up these logic gates, essentially. And these exact same logic gates that you can use to program a Minecraft calculator are the exact same things that are actually in your CPU running your machine and your computer. I don't know if anybody plays Magic the Gathering out there, but you can actually turn Magic the Gathering into like logic gates and stuff. I believe if anybody's played Dwarf Fortress, you can turn Dwarf Fortress into a computer using gates and water flowing and stuff like that. Yeah, all kinds of craziness. And this is what's actually underneath there. So this is why, you may be doing computer science. I mean, like me, honestly, I'm not a big hardware person, but you need to know how this stuff works because it really is the fundamentals of computation here. And then you could get below that of like, this is how, I believe in the lower right is a flip-flop if my memory serves correctly. And I think this is how you store values in hardware and all kinds of craziness. This is like really getting into the complexities of how you combine these incredibly simple gates that just do very simple things to do complex things. It is a flip-flop. All right, thank you, Zion. See, this was crazy. I remember, I haven't really thought about that in, Jesus. No, I don't want to tell you when I took my architecture course in undergrad, but yes. It's been a while, let's just say that. Cool. So, okay. So, we want to zoom back out, right? So that was kind of zooming into the CPU level. But at a very high level, CPUs are actually very simple. And this is kind of the gift and the curse of programming, right? The kind of the best way I've heard it described is programming a computer is like trying to tell a very, very stupid but very fast butler what to do. And so so you have this CPU that's going to do exactly what you tell it to do, right? It doesn't guess what you want. It can't read your mind yet to understand your intentions behind what you did. And probably you've realized this so far in using a computer, right? If you tell it to delete a file, it will delete that file. It doesn't say, oh, but maybe this is a special file, or you need this file next week. This is the assignment you're turning into class. It's just going to delete it because you asked it to delete it. And that goes kind of all the way down the computing stack. So what we're going to do is think about at this level, the CPU is going to execute some code that we give it, and we're going to actually be programming it here. And its job is to kind of, it will be able to compute things, add things, multiply things, divide by things, all those kinds of things, all that stuff. And it has to then be able to fetch data from memory. So as we'll see, the CPU itself has some storage on it, so you can actually do computation on the physical like silicone that exists in the CPU, and that's insanely fast. So being able to execute things inside the CPU is incredibly fast. But the amount of storage on there is very limited. And of course, we want to run, Google Chrome, which takes up 3 gigabytes of memory. That's not going to fit inside your CPU. So we need some place to store that. So we have memory. Memory you can think of as what's known as like volatile storage, right? So this is memory that can go away, right? When you turn off your computer, the memory disappears, goes away, and does not persist between reboots. This is in contrast to your disk. So your disk that you're reading and writing from is persistent storage at the cost of being much slower. So I can't remember the exact, if somebody can, there's a great diagram or infographic or something that kind of lays out the different latencies, how long it takes to access, a data when it's in a register versus in what's called the L1 cache, which is one cache layer in your CPU that tries to make things faster, L2, L3 versus memory versus disk versus network. I think it's roughly on the order of either tens or hundreds of thousands times slower. So registers versus memory versus disk, I think it's roughly somewhere within there, either 10 times to 1,000 times slower. So you can see that actually multiplication adds up. So going from the CPU, accessing something from memory from disk, it's pretty crazy. And so but the CPU's job is really, when you think about it, just shuttling things in and out, right? It does some computation, it takes things from memory, it puts things on disk, it asks for networking. Yeah, thanks Zion for putting that in the chat, much appreciated. And so what's really going on is kind of inside the CPU you have a bunch of stuff, and there's and actually what we're learning now is actually technically a fiction of modern CPUs. So if I can peel back the curtain just slightly a little bit, what we'll see, the x86 instructions we all see of moving memory from one register to another is actually a fiction. So what actually happens is there's another layer where your assembly instructions get essentially compiled and translated down to microcode, and that's what actually executes in the CPU. So it's insanity. So yeah. Anyways, this so there's registers. There's ALU stands for arithmetic logic unit. That's the thing that adds things together. I don't know what CU is. Does anybody know what CU in this diagram should be? I can make something up, but I don't really want to make something up. And then, like we said, there's caching. So there's essentially caches. You can think about store data so transparently to your program. So if your program, you can think of if it's frequently asking the same memory locations rather than the CPU going all the way to memory every single time, if it can actually store that value locally on the chip in a cache, it'll be much faster to fetch from. CU, control unit. Okay, cool. Thank you. So something that probably controls where we're at, does any of that stuff. And then this then gets even more complicated when you now have multiple. So modern processors or old processors, you just think had one CPU that was executing, but we've actually hit a limit on how fast we can make the processors, mainly due to heat. So we're now generating so much heat that we can't make the processor actually go faster and execute more instructions per second. So what we had to do is say, okay, rather than putting just one processor on a chip, what if we put two processors on a chip so they could execute concurrently? And that, as you'll find in your programming careers, opens up so much problems in concurrency. You have multiple things running at once, accessing different things. This is a source of a lot of vulnerabilities in terms of race conditions, where you're trying to race for access to different things. And you have this craziness where each CPU core itself, so this is the black lines within here, that would be one core. The core has its own L1 cache, and there's an L2 cache that's shared across cores. There may be an L3 cache, all kinds of cool stuff. So anyways, any questions on kind of like this modern CPU architecture and computer architectures? Cool. All right. And yeah, so what we're going to be looking at here is the what's called the von Neumann architecture. So von Neumann is one of the people that is kind of considered the fathers of modern computer architectures. But we will skip that and move on to the next slide. Question in the chat is, what's next for CPU? That's a great question. I have no idea. I'm not a hardware person. I'm trying to remember what people have told me. I mean, the main thing they're doing now is shrinking the size of the transistors on a chip to smaller and smaller things. I think they're down to like 5 nanometers. And every shrink in that reduces the heat, which means you can go faster. And fit more things on there, so you can fit more cores and everything on there. Yeah, I mean, the crazy thing is seeing a company like Apple design their own processors, right, and their own CPUs. So that's what's insane. There's also talk of like, I don't know. Yeah, I mean, I don't know. The main thing is dealing with power problems. So there's all kinds of like dealing with power and crazy stuff. So, okay, where are we? All right. So now we're going to go to x86-64 assembly. And the crazy thing to think about is this is true. The assembly itself, like the assembly language is the language that the CPU talks. And it's as far as we're concerned. So Like I said, this is actually technically a fiction with modern processors, but that's neither here nor there. That's the contract that the CPU says that says, okay, if you give me an instruction that looks like this, I guarantee that will happen. Whether I do it in exactly the way you think or not is not your concern. And so we will be thinking about in terms of instructions. So we'll write basically code that will do things, code that manipulates data, code that compares things, code that changes the control flow. And the other thing we'll look at is system calls. So what did we learn about system calls already in a different context? What was a system call? Yeah, so exactly. Thank you, Redgate. So a system call allows a process to ask the operating system to do something. Remember, as we talked about, a process basically can do very little on its own. It essentially can't do anything on its own. It actually needs the operating system to do that. And as we'll see, yeah, it's an API. That's a great way of, so API, application programming interface. So it's a way for the process to ask the operating system to do things on its behalf, like open files, write to files, read to files. We'll actually get into all that, read or write from the network. And so we'll see how that happens. So some other concepts, registers. So these are the things that hold values inside of our CPU. And we'll also look at memory. So memory of our program, the stack, other things mapped in. Okay, so registers you can think about are very, very fast temporary stores for data. So they're temporary because, like we said, they literally live on the chip. So if the power goes out, you will lose what is currently in the CPU. But it's incredibly fast because it's right there on the CPU. So there's a bit of a historical progression here. Like 8085 and the 8086, these are different like families of chip architectures. So you had an A register, a C register, a D, B, E, H, and an L. There must have been a B here because there's definitely an x86B register. So I don't know why that's not on these slides. Somebody yell at Jan for that. And then as things expanded, so I believe the 8086 was a 16-bit machine. So what that means is essentially each of these registers here, AX, CX, DX, took up exactly 16 bits of memory. So the highest value you could hold in there was 2 to the 16th minus 1. Oh, EBX is here. Okay, cool. Why isn't it in the order you would expect it in? Why is B here and not here? That's silly. And then x86 extended that to 32-bit. So if you see some kind of older-ish style programs, you'll see these things in here. EAX, ECX. The E stands for extended. So you can think of this as the extended AX register, the extended CX register. And then Jan has it here, AMD 64, but I usually call it x86-64. So this is a it's an extension to x86 to allow it to be backwards compatible. So x86 programs will still work while running on an AMD 64 chip, but it's extended where so I didn't say how x86 was extended. x86 is extended to 32 bits. So every register here is exactly 32 bits and can hold that much values in there. And then finally, x86-64 extended that to 64 bits. So and then it also added different registers here. So we have kind of some interesting ones that we'll eventually get to are like SP and BP, so the stack pointer and the base pointer. It doesn't. Oh, he does have this here. Okay, good. And then I guess just for comparison, is ARM, but ARM is different, like has these R0 through R14 registers. There's also various extensions that either add other registers or add other functionality. So you can think about this as like, Intel's making chips, right? They want to, let's say, actually one of the big things that's important for security is, do you want cryptographic operations like encryption? Do you want them to be slow or fast? What do you think? Fast. Yeah, so when you're encrypting something, right, or decrypting something, if it's slow, then who's going to enable encryption, right? One of the goals of privacy and security in general is to make sure that, like, let's say our communications across the network are always encrypted. But if it's incredibly slow and adds latency, users hate that, and it's actually terrible. So you want encryption to be as fast as possible. So software can do encryption, right? You can implement the algorithm for AES is one of the encryption standards. So there's software libraries that do that. They can use all these registers, use all the instructions here, and execute all the crypto operations. But wouldn't it be great if I had an instruction in my machine that just says do this encryption operation? And then it could do it so much faster because the hardware could be dedicated to do it, and it doesn't have to wait for loading any data from software. The software doesn't have to be involved. So this is kind of the point of these CPU extensions, to add these features that don't always exist, but the software has a way to probe for it and ask the CPU, hey, do you support offloading crypto operations? And if it says yes, then it knows it can use those instructions. Otherwise, it uses its slow normal algorithm. What's the problem of like putting, let's say, like an encryption stuff in hardware of a CPU? People typing ... in the chat. Maybe they should have been practicing typing, then that way they could have been done faster. Yeah, good comment, Devil's Canyon. So hardware flaws in the CPU itself that might lead to side channel attacks. So I'd even erase the might lead to side channel attacks. I'd say hardware flaws in the CPU. So if you have flaws, it can be a massive pain to actually update the hardware. Other thing I think is longevity of cryptography algorithms. So DES used to be the main standard of encryption, but now it's actually been deprecated because flaws have been found. So once you dedicate kind of that space in there, why have, and then you could have problems later on. Yeah, so it's definitely, and it's definitely not a panacea. The Spectre meltdown it didn't take advantage of any hardware flaws to attack hardware cryptography applications. It actually allowed, the main thing of Spectre meltdown was to allow a process to read memory of either the operating system or another process, which is definitely bad, but wasn't exactly having to do with hardware flaws in like a cryptographic algorithm. Cool. Okay, and we'll go over the basic kind of functioning of a CPU later. But essentially, we need to know where in memory we're trying to execute code, and so that's different architectures do it differently. In the address of the next instruction to be executed is stored in a register. And this is on x86. It's the register EIP, so you can think it comes from 8086 of IP. And then RIP is the x86-64 version of that. Cool. Okay, so registers give us ways to access things. And you may think, Adam, you just wasted our time by showing us this insane diagram of all these different random letter combinations of AX and EAX and RAX. Why do we care about any of this if we only care about RAX? Well, software and computers in general are complicated. Sometimes they do things in ways that may not necessarily make sense. And so by historical reasons, so you can, I believe, probably still run programs written for an 8086 on a brand new x86-64 processor because it's all backwards compatible. So you can actually partially access different parts of the register. So the way to think about a register, if we're talking about x86-64, in this diagram, it's RAX. It's this all the 64 bits of that RAX register are physically somewhere on the CPU, and you can actually think about those ones and zeros. Usually when we're thinking about these things, we break them up into bytes. So a byte is composed of 8 bits. So that's what the vertical lines here separate. There should be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. So 8 cells here that each of them fits 8 bits or 1 byte. And so you can actually reference some of these parts of a register. And so it's really important when you're, let's say, trying to understand a program and trying to reverse engineer a program from the assembly code itself to see, oh, they're moving 10 into AH. And then you have to know, okay, AH is not its own register. It's actually the second lowest byte of the RAX register. Similarly, the AL register is the lowest byte of RAX. AX is the lowest 16 bits or 2 bytes. And the other way we can say 2 bytes is a word. So AX is a word. Is all of this stuff very confusing? Definitely yes. I almost never use the word determination because different systems actually I believe there's different systems where a word is different sizes. And so I don't know, just I guess my own personal biases and backgrounds, I almost never use that. I usually talk about bytes. So I'd say AX is 2 bytes long or a word. EAX is 4 bytes or a double word. And RAX is 8 bytes or a quad word. Cool. And then this naming scheme extends to RAX, RBX, RCX, RDX, RDI, RSI, all those other registers that we looked at. Any questions on this insanity of see, this is where I get to correct Jan's slides in real time. It's actually not due to a historical oddity, so yeah, the idea is in here is if you move data into, let's say, EAX, the only thing that changes are the lower 2 bytes. Everything else in this register remains the same, except for EAX. If you move 10 into, let's say there was all ones in RAX. So RAX is 1, 1, 1, 1, 1, 1, 1. And if you move 10 into EAX, it will zero out everything in RAX. And this is not a historical oddity. This is because so that you can run x86-64 programs on, so you can run x86 programs on x86-64. Right? It makes sense, actually, when you think about it like that, because how could you run if you had so the long term in the future, looking forward, we'll actually realize that the value of -1 is represented by all ones in a register. So if I were to move -1 into EAX, that would fill all ones there. And then if I'm moving 0 into EAX, that would actually, if that only changed the lower 32 bits of EAX, of the whole RAX register, then I'd still have the upper 32 bits being 1, and that would completely mess up my calculations, and it would not be backwards compatible. So it's actually due to backwards compatibility. Okay. I think I've actually told this to Jan. This isn't just random stuff I'm pulling out. And these are all the different registers for RAX, RCX, RDX. Honestly, you kind of just have to look them up. The only ones I know are RAX through RBX. I think I know RSP except for these ones, the highs and lows. I definitely would not know what SPL and BPL are off the top of my head. And the other ones I basically just look up on demand. Like if I actually need this information, I will look it up and try to get there. And okay, so instructions. So the general form of instructions are the opcode. So the opcode tells the CPU, hey, what do we want to do? Remember we talked about there's different things. Do I want to move data around? Do I want to try to fetch data from memory? Do I want to add something to something else? Do I want to subtract something, multiply, divide? There's actually like x86 is an insane architecture where it has so many instructions, some of which I've definitely not seen before. And so then you first have your opcode, and then you'll have an operand followed by a comma, followed by another operand. And so the operands are basically, so like our programs, you can think of like opcode is kind of like the program that you're calling, and the operands are the arguments that you're passing to that. And the way to read this, so highly recommend use some kind of reference material. So here's the reference material that Jan recommends. I'm sure it's great. And so let's look at the move instruction. So MOV. So it should, let's see. And where did my cursor go? Oh no, my screen is being observed. Scary. Okay. So this is anybody scared yet? So move, you really don't have to get too deep into this yet. This actually shows you like the actual ones and zeros of the opcode, the bytes. So move would be A0, A1, A2, A3. These are all different types of move. I guess it just says move. I guess move S is move a string. That's crazy. I did not know. Nope. Okay. There we go. Move. Oh, we did already look at that move. Okay. Cool. So the way to read this is we're going to use Intel syntax because apparently everyone has a conniption when they actually use different ones, even though like most things, it actually doesn't matter. It's just you can move between them at your will. So what this instruction said, and so the way to read this syntax is you have the opcode is move, and the very first thing is usually the destination for something like this. And so the second operand is the source. So this says move whatever's inside the register RBX into RAX. So the way I always think about it and the way I always try to parse and think about the x86-64 instructions in my mind is what should be the case? What should happen after this instruction? So we talked about RIP, the instruction pointer. So let's say the instruction pointer has a value which will point to memory, as we'll see. And then the instruction at that memory address is move RBX into RAX. And so after that instruction executes, what the CPU guarantees us that will be true is whatever was in RBX is inside RAX. At this point in time, do we know what is now inside the RAX register? No? How come? Yeah, exactly. We don't know what RBX is, but we do know one important piece of information that's already mentioned here. We know that after that instruction, whatever was in RBX is now in RAX. And then the next line, after I lock my computer again, is we're going to add 1 to RAX. So do we know now do we know anything about RAX? What's inside of it? Yeah, it's RBX plus 1. Thank you. Great. And the other thing here with an instruction like add, so if you think about add as a mathematical equation, so you're adding two elements together, right? Here we're adding the constant 1 to whatever's inside RAX. But where do I put that result? Shouldn't, like, if you had an equation, you'd say x is equal to RAX plus 1. So where do I put it? Can I put it in 1? Good question. Yeah, so it's basically implied here that we'll take RAX, we'll add 1 to it, and we'll put it back in RAX. So somebody had a question of what would happen if RBX was all 1s. So if you had all bits of 1s and you added 1 to it, you do, let me see, we can maybe try to do something here. Although, honestly, I can't see my cursor for some reason. That's what was going on. This is weird. Oh, this is bonkers. Okay. T? No. T does not move anything. Oh, is it like this? There we go. Of course, I'm going to switch to the amazing EMATs. Okay, increase the font size. So let's say we have, and just for simplicity of arguments, so let's assume this is just 8 bits. So we only have to deal with, or 1 byte. So we only have to deal with 8 bits. So if I do this plus 0.0000001, right? We're kind of asking what's the result here. So it's just like the math you've basically been taught about, right? So what's 1 plus 1 in binary? In binary, is there a 2? Yeah, binary means we literally only have 1s and 0s, right? So just like normal base 10 arithmetic, we don't have one digit that represents 10, right? We have to represent 10 as 10, and what this means is 10 times 1 plus 0, which is equal to 10, whereas 20 means 10 times 2 plus 0 is equal to 20, right? So we multiply this by 10, and we do the same thing for 453. We would say this is, the highest place is 100 times 4 plus 5 times 10 plus 3, and that would give me 453. So similarly with the 1s and 0s. So if we have this in binary, so this represents, so it's 2 to the 1, and actually I should have probably done that. It's exponentiation, but that's fine. Times 1 plus 0 is equal to 2. And 1, 0, 0 would be 2 to the second times 1 plus 2 to the first times 0 plus 2 to the first times 0, and this should be 4. And doing this is insanely tedious, and that's why we have a great calculators that can do all this stuff. A lot of the calculators have programmer mode, which is what I believe this is in. So we can see how things are represented. This is by default hex. You can translate between the different bases. So hex is hex has a base of 16, decimal has a base of 10, and binary has base 2. Okay. So back to our example. 1 plus 1 is... One plus one is, yeah, in binary it's 1, 0. Decimal it's 2, right? So it's 0 carry the 1. So just like normal arithmetic, we carry the 1. 1 plus 0 plus, or sorry, 1 plus 1 plus 0 is same thing. 0 carry the 1. 1 plus 1 is 0 carry the 1. 1 plus 1 plus 0 is 0 carry the 1. Yes, if you're wondering, I am going to do this for all of them. 1 plus 1 plus 0 is 0 plus 1. 1 plus 1 plus 0 is 0 carry the 1. 1 plus 1 plus 0 is 0 carry the 1. 1 plus 1 plus 0 is 0. And then where do I put this carry? So I do have that carry, but where do I put it? How many bits do I have in my registers that I said in this made up thing to make this easier? How many bits do I have here in my registers? 8. So I can only store 8 bits. How many bits do I already have? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. I already have 8 bits. I don't have space for 9 bits. I only have space for 8s. So this actually gets essentially discarded. I think a flag gets set somewhere to say that there was an overflow, but it essentially gets discarded, and the result is all zeros. So you can think of this as actually having like wraparound arithmetic, right? So the highest number you can possibly have, which is composed of all ones, if you add one more to it, you wrap back around to 0. Cool. All right, so we can add one more to RAX. That's where we were on that example there. Oh, there we go. I got my cursor. Maybe it's back. And yes, okay, that's handy. Wow, that's a great prank. Cool. Then the CMP instruction, compare. So compare RBX to RAX. And what this instruction does is set a bunch of flags inside the CPU that are used in this JB instruction. And I actually don't know what the B stands for. Could somebody tell me what JB actually means? This basically is a control flow instruction. So this says, hey, if this condition, whatever that B condition is true, go start executing at some location. So this will be some memory address, and the CPU will then change its the RIP register, which is where it fetches the next instruction from, and then starts executing from there. If that condition doesn't hold, then it jumps to the next line after it, and will start just executing after there. Jump, it can't be, oh, jump below. That makes sense. Yes. So jump if less than. Great. So jump if RAX is less than RBX, I think. Cool. Awesome. And we can also, now, all right, this is going to require some, oh, here it is. This is the crazy JB. So jump if below unsigned. So signed versus signedness we'll get into later. Okay. Cool. So yeah, we can let's follow the logic here. So let's move RBX into RAX. Now the one thing we didn't talk about is this bracket. So this bracket is how we access memory. So what this says is whatever's compute the value RBX plus 4. So take RBX, add 4 to it, and then go to that memory location, grab whatever's there, and copy that into RAX. And so this is how we're actually fetching things from memory, and we can bring data from memory into a register. And then we can compute something from there. So we can add RBX plus RAX. We can multiply RSI. I have to check up. I don't remember the semantics of the multiply instruction to remember where exactly they put the values there. But we can multiply something in there. And then increment, INC is increment. So this is increment RAX. So take whatever's in RAX, add 1 to it. Then increment with a dereference. So with the brackets, says go to wherever RAX is at its memory location, fetch the value, add 1 to it, and put it back, I believe. Cool. Okay, lots of craziness. These are all the flags that get set. You can check these later. We won't go into them so much right now. What I want to get us to is to start writing some x86. Okay, cool. So we're going to stop here. Okay. Yeah, so this is actually the important thing of where I want to go, because we're going to, I want us to start writing our first Hello World program. So the important thing to get the program to do something, like we could write some x86-64 programs right now that move data in between registers, but it's not really that useful because we can't really see what's going on, right? We want to actually see some input and output from our program. And so this is done through actual system calls. So we can use the man syscalls. We can look, you can look at the syscalls. Oh, cool. And then every system call, so this is the important thing to remember, is documented in section 2 of the man pages. So to access that, you want to do man to open. So if you know you're looking at some system call, like some crazy system call like open at or clone, I think is a crazy one, you can do that here with man to clone or open. And so on x86-64, this is the conditions that we have to satisfy in order to call a system call. So we'll need to, again, we can't, we have to have some way to ask the operating system, hey, do this thing on my behalf. So we need to put the number of the system call, we'll look at how to see that in a second, into RAX. So RAX register will have the system call number. We then we'll need to store arguments in RDI, RSI, and there's actually, depending on the argument, what register. So we put all of everything we need in registers, and then we execute the syscall instruction. And then that will, at that syscall instruction, that is actually what goes from our user process into the kernel, does something, and then returns to right after that system call. So let's try that out. Okay. So here, actually, okay, so just by convention, most assembly programs have a .S extension. I actually don't know exactly where that comes from. Kind of interesting thing there. But okay, first thing we want to do is tell this thing that we're using Intel syntax. So this is how we can use different kinds of compilers. There's all kinds of things, or technically it's called an assembler that takes your assembly code and turns it into actual binary code. For now, so in the syntax that we're using, everything that begins with a dot like this, like .intel_syntax, this is telling the CPU, or telling the assembler, hey, I'm going to be using Intel syntax, not AT&T syntax. No prefix is also nice. This makes it easier for us and means that we don't have to, when we're doing memory operations, say the size. It will try to infer it. Okay, the other thing that we'll need to do in terms of yes, okay, .text globe. Cool. The other thing we'll need is a directive. So everything that begins with a dot is called a directive. Here, the .text directive says, hey, everything after this, I want to be in the text section, meaning it's going to be code. We'll see, because there are places where we want to store data and all this other stuff. And then .global means it basically means export this as export this symbol main. So we'll define a location called main, and essentially all this jazz basically is going to tell GCC, our compiler, hey, we're going to want to execute this main function first. So the very first thing I want to do, if we remember return codes, let's look up man to exit. Exit, terminate the calling process. We can call exit, put in a status, and let's see. The function exit terminates the calling process immediately. Any open file descriptors belonging are closed. Any children, blah, 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 stuff happens. Okay, cool. The value status and 0377, we can ignore that, is returned to the parents to the process as the process's exit status. Remember, we talked about programs has exit status and a return code, and this is something that we can use to see the status. So this is one of the ways that we can set that, is through this exit system call. So let's write a program that, so I believe, I can't remember. Is that, no, I think I can have C style comments. Yeah. Okay. So / comment. Okay. So I want this purpose program call syscall exit. Somebody give me a number quick. Here's a terrible random number of machines. 5 is the one I saw. Cool. Exit 5, right? That's what I want to see. All right. So like the slide said, the conditions I need to set up. So I need a system call number in RAX. I need to figure out the system call numbers. Luckily, if you just look up for I do x86-64 system call numbers Linux. And again, this is where it's really important. Remember, this is a way for a process to call into the, Ryan Chapman has a great Linux system call table here. Remember, this is a way for a process to execute and ask the operating system to do something on its behalf. So very clearly what that should mean to us is, hey, this means that if this is operating system specific. If you run this on Windows, it's not going to work. If you compile this and run this on Mac, it's also, well, it actually may work. It will likely work because it's a Unix thing, but it may or may not work. It's not guaranteed to work. Would it work? No, I don't think it would. So we can look at the system calls. We see read, write, open, close, stat, fstat, lstat, poll, lseek, mmap, mprotect, blah, 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 blah. What I want is exit, so I'm going to search for exit. It is 60. So the value that goes in RAX will be 60, and then the error code will be the first argument. Now I need to use the top of this, so I probably should have picked a better one. But so this is saying put in RAX the value 60, put in RDI, our exit code, and then call a syscall that will ask the operating system to quit our process and set our return code as whatever we put in RDI. So do you think we can do this with the information that we have so far? So I want to move, let's say I want to set up RAX first. So what's the destination? Yeah, what do I want to move in RAX? And then I need my first argument to go into RDI. Yeah, it is the opcode. I was going to wait until the end. So what goes in there? $60. Yeah, we just looked that up, right, in that table. So we're going to move 60 into RAX. Do we know what the value of RAX is before this instruction executes? No, we have absolutely no idea what's the value in any of our registers, right? We actually can't make assumptions, except for a few cases, but we won't talk about them right now. But for the most part, we don't know what's in any of these registers. Okay, so we set up RAX. Now, what would happen here if we just did syscall? So syscall is how we call the operating system. So this would tell the operating system, hey, I want to exit what's it going to use as our exit code? Exactly. Boom. Thank you. Whatever's in RDI, right? So whatever happens to be in that register, just whatever bits are there, it interprets as, yep, this must be the return code, right? The operating system has no idea that we didn't set it. All it knows is that it's not set. So we need to make sure to set it. So we want to move into RDI. What was the value we wanted to put into RDI? 5. Cool. Now we can go, hopefully that's here. Oh, of course it's not. All right. I turned off a Dropbox to make this easier and better to transfer stuff. Okay. Cool. So I have this program. Now I can actually just use GCC to compile this. So GCC is a compiler. You can use to compile C programs. It will know, I think, I don't want to say based on the extension, but I think based on the extension that this is a assembly file. I should be able to run that. Look at my directory. I see that it created by default a.out. I can, now this is something we hadn't talked about yet. We'll get there eventually, but in order to execute this a.out program, because it's in my local directory, I need to do /a.out. And how do I see if it was correct or not? How can I validate that it was 5? Yeah, thank you. Echo $? Right? $? is the exit code of the previous command. Boom, 5. There's also another way I can do this. So strace is a super useful command. strace allows us to trace system calls and signals. So this will actually show us all the system calls. So you think about that, like I talked about, right? System calls are a way for a process to ask the kernel to do something on its behalf. And the cool thing with strace is it will essentially sit in between there and show us everything that's happening. Now, there's a lot of stuff. It's this execve, this break, all this stuff is executing. It's loading things and doing all kinds of stuff. That's okay. Just, you can kind of scan through this if you're really super interested. You could go look up all of these system calls, right? You know these are system calls. You can do man2 access, man2 openat, man2 fstat, man2 mmap, man2 close, man2 mprotect, right? But we can kind of ignore that. And at some point, it'll get to our actual program's code. And here we can see this beautiful, beautiful exit 5. And if I go back here, so a bit of a question, test for you. What happens if I swap these two lines? What's going to happen? What do you think? Do we want to bet? Is it going to work? Is it not going to work? Is it going to blow up? Yeah, why do we... So people are saying it's the same. Why do we think it's going to be the same? before I hit enter. Yeah, the question you want to think about is at this line, so right before the CPU executes system call, what is the state of the registers that we care about, right? We care about the register RAX. We have to have the value 60 inside the register RAX. And we have to have the value 5 into the register RDI. If that condition is true, which will happen no matter what order this move executes in, then it should be just fine. Boom. We see this 5, and we see that the process exited with 5. What if I did... So, why I like to set up RAX first? Why do I like to set up RAX first? For me, it's very nice. Why is that nice? Not A before D, although that's an interesting idea. And you also got to worry about because there's an RDX and an RDI, which is super annoying. Yeah, so from a conceptual point of view, when I'm reading this as a programmer, right, the thing that defines what the arguments to the system call is the system call number. So the most important thing here is that system call number. So what system call number is it? And then after that, then come the arguments. So this is actually kind of a natural way of writing this. Cool. What if I did move 60 into EAX? Is that going to break it? Like I didn't set up RAX, and I have to set up RAX. Yeah, it'll be fine. Why will it be fine? Okay, it worked. Why did it work? Yeah, 60 is not very big, so I can move that into RAX. So if I look up here and I look at my calculator, I turn it into decimal mode, I type in 60, I can actually see the bits, the ones and the zeros here, right? So this actually fits in a word, so 2 bytes, but it definitely fits into 32 bits. So I'm overwriting EAX, and as we talked about in the slides, due to that crazy, I don't even have to worry about what's in the upper 64 bits here, because when I'm copying 60 into EAX, it will automatically for me zero out those top registers. So I am guaranteed that after this instruction executes, the value that's inside EAX is going to be 60. I believe I should be able to do the same thing with EDI. Yep, exit 5. Awesome. Cool. All right, we just started our journey here. What I think would be super useful for you all is to like reproduce this. So make a make something that calls exit 1337. Right. So figure out kind of how to do that. And that way you can start doing this on your own machine. I'll end the meeting here because I got to go set up some stuff for later. And then from here, we'll go from here and we'll extend our programming of x86. So this is x86-64. We'll do a hello world. We'll start off by doing a hello world. So look up the instruction LEA, load effective address. That's a really important one. And yeah. We will go from there. Cool. Questions? All right. Goodbye, stream.